Hey everybody, it's Mr. Carr again. Today we're going to continue with our solving. We get to use a little bit more algebraic skills as well as some identities to help us solve. Okay, so we want to find all of our solutions of 2 times sine squared x plus sine of x minus 1 equals 0 on the interval 0 to 2 pi. The thing to recognize about this one is we're basically working with a quadratic. So if I think of this, if I call it, I'm going to call it a. If I say that a is equal to the sine of x, for example, then I'm trying to solve 2a squared plus a minus 1 equal to 0. Now, you can do this with factoring or quadratic formula. It's your choice how you want to do that. I'm going to go ahead and do factoring because it's not too bad to do this one. So, for example, 2a squared has to come from 2a times a. Negative 1 has to come from a positive and a negative 1. With this being a positive a here, I'm going to have a plus 1 and a negative 1 like this. My normal quadratic solving means I'm going to take this and set them both equal to 0. And then that's a plus 1 equals 0. Okay, so I solve this out. I'm going to add 1 to both sides so that 2a equals 1, divide by 2, and a equals 1/2. Over here, I just subtract 1, and a equals negative 1 here. But the thing to remember is I'm not dealing with a, I'm dealing with sine of x here. So I replace that back in there, sine of x equals 1/2, and the sine of x equals a negative 1. So the question is, which values from 0 to 2 pi are we going to get? So from 0 to 2 pi, where are we going to get these values of sine of x here? Okay, so for my or I'll just put them all in the same thing. Okay, so I'll model this one here. Remember, this is opposite of our hypotenuse. So that's going to happen in the first quadrant like this. Okay, so that's going to be 1 and 2 right there. It's also going to happen in the second quadrant because this is the other positive one. So that'll be 1 and 2 there. Now, when is sine of x equal to negative 1? That happens at the quadrantal angle right here at 0, negative 1. Okay, so it's that sine of x, and that's the only time it happens on this specific interval. So if I figure out what my reference angles are, with the 1, 2 like this is going to be pi over 6. It's also going to be pi over 6 here, so that means going from all the way around to that one. That's going to be an angle of 5 pi over 6. And my last one is down here. This quadrantal angle is 3 pi over 2. So that means I have 3 total solutions here. For the x equals 1/2, that comes from pi over 6 and 5 pi over 6. And then the sine of x equals negative 1 comes from 3 pi over 2. Okay, so that's using our factoring or quadratic formula to help solve for this one. I like basically taking out the sine of x and then plugging it back in to make it work out that way. All right, find all solutions of this equation here. So this is one of the ones we're going to use our trigonometric identities to help with this one. Notice how we have sine squared and cosine squared. Okay, so one thing that you can do is you can rewrite either one of these using like we'll use this version. We'll do sine squared x plus cosine squared x equal to 1. So I'm going to rewrite this one because this side has sine of x in it. So I want to keep everything in terms of sine. So that means this is the same, cosine squared of x is going to be the same as 1 minus the sine squared of x here. Well, since it's a quadratic, we're going to treat it like that. I'm going to go ahead and start bringing things together. So for example, I can subtract 1 to both sides. I can also add sine squared x to both sides. Okay, so when I do that, this is actually going to be all gone now. This will be gone. I'm going to get, so that's a plus there, 2 times the sine squared x minus the sine of x equals 0. Now I could go through and do like that substitution idea, like a equals sine of x here. Instead, I'm just going to recognize that I can factor out a sine of x. So I'm going to be left with 2 times the sine of x minus 1. That's equal to 0 there. When I separate these, I get sine of x is equal to 0. 2 times the sine of x minus 1 equals 0. We're going to take our last couple steps here so that 2 sine of x is equal to 1. And we divide both sides by 2 so that sine of x equals 1/2. All right, and so just like we did before, we're going to look at when is sine of x equal to 0 and when does sine of x equal 1/2. So it happens in 4 total places. Okay, so when I model this here, I'm going to get this point here is at 1, 0. There's my sine of x equal to 0. It's going to happen here. It's going to happen at pi over 6. It's going to happen over here at 5 pi over 6. And it's going to happen over here at -1, 0. Okay, so it's happening at 0 degrees or 0 radians, I should say, and at pi radians as well. So I got 4 total answers. I've got x is equal to 0, pi over 6, 5 pi over 6, and pi as my 4 answers. Okay, so this one is going to be another little tricky one to it because we're going to use our identities again. We're going to solve this one by squaring. We're also going to want to check for any kind of extraneous solutions. So we got to be careful when we work through these problems because sometimes we're going to get that. So for example, on this one, I'm going to start by adding cosine x to both sides. So it looks like this. The sine of x is equal to cosine of x plus 1. I like to keep things in terms of our Pythagorean identities. So I'm going to rewrite this by squaring both sides now. So if sine of x equals cosine of x plus 1, we can square both sides to turn into sine squared x is equal to this one squared. So remember, we are distributing this. This is going to be cosine of x plus 1 times the cosine of x plus 1. So I need to distribute here. So when I do that, I'm going to end up with cosine squared x plus 2 times the cosine of x plus 1. Okay, sine squared x, I'm going to rewrite this here. Okay, that one, remember from our Pythagorean identity, that's the same as saying 1 minus the cosine squared of x. That'll equal to cosine squared x plus 2 cosine of x plus 1. And then we can start combining things together to get it equal to 0 since it's technically a quadratic. But look what happens when we do that. If I add cosine squared x over, I can subtract 1 over. This will 0 out. And I'm going to get 2 times the cosine squared of x plus 2 cosine x. And that's it for that one. And then these are gone here. All right. So I can go ahead and go into some factoring. Since this is 2 times cosine of x, cosine squared x, 2 times cosine of x, I can take out 2 cosine x. So I'm going to be left with a cosine of x plus 1 in there. Okay, so when I solve both of these, we get 0 is equal to 2 cosine of x, divide by 2, and I'm going to say 0 is equal to cosine of x, and then cosine of x plus 1 is equal to 0, so the cosine of x equals a -1. So here's where some of the trickery comes into play. Gonna go ahead and figure out where does these all happen. Cosine of x equal to 0, so we're only going to deal with quadrantal angles here. So the cosine of x equal to 0 is going to happen at, right here, it's going to happen at pi over 2 and 3 pi over 2. Okay, so that is going to be 0, 1 and 0, -1. Okay, so that's my two answers there. X equals pi over 2 and 3 pi over 2. For cosine of x equal to -1, that's going to happen only at this value. Okay, so that happens at one spot, that is pi right there. But here's where we have to be careful. We got to go back to the original equation and see which ones happen. I would say you want to double check for extraneous solutions because what we did was we squared this. Any kind of negative values here will always turn out positive. So because of that, we might create extraneous solutions. So I'm going to go ahead and do a quick check of the original equation. Let's do that. So I'm going to do the sine of pi over 2 minus, sine of pi over 2 minus the cosine of pi over 2 here. Okay, so sine of pi over 2, you've already got it on here. It's going to be this one. Sine is going to be 1. That's going to be minus the cosine, which is 0, and I get 1 as an answer, and that's what I'm looking for. So this one checks out. Pi over 2 is good. So then I do the same thing with pi. Sine of pi minus the cosine of pi. Okay, sine of pi is going to come out to 0. Cosine of pi is -1, but when I do 0 minus a -1, that turns into a +1 now. Okay, so that one checks out as well. But when I do the sine of 3 pi over 2 minus the cosine of 3 pi over 2, I'm going to get a -1 minus 0 here. So I get a -1 as an answer, which means this is extraneous. So my final answer is only two solutions. It is x equals pi over 2 and pi, and no other ones. Okay. All right. we're gonna look at some more tricky ones. These are some fun ones we got going on here. So solve on the interval of 0 to 2 pi, we're looking at sine of 2x is equal to root 3 over 2. I don't have to take any steps here, and this actually applies to something we'll learn about in a future lesson. But for right now, we still want to think of it this way. What if I just said the sine of theta equals root 3 over 2? So let's figure out where that happens. So in this scenario, that would normally happen in the first quadrant. It would look like this. Okay, be root 3 and then 2, and it happened the second quadrant like this. Root 3 and 2. And my angles, as we've seen before, is going to be pi over 6 and 5 pi over 6. Okay. Sorry, you know what? I just realized I did that backwards. This is sine. I got used to doing it this way. Sine is going to make it this way. So it's actually going to be pi over 3. Okay. That is going to be opposite over hypotenuse. So root 3 over 2. And then over here, root 3 over 2. So this is pi over 3. And then 2 pi over 3. My bad on that one. Okay. So that's our normal ones there. But the thing to remember is sine of 2x means we have we have a shortened period, basically. My period of this kind of function is going to be 2 pi divided by 2, which is pi here. So that means I'm actually going to go through in like kind of comparison. This is my normal time I would do it, but in this case here, I'm going through 2 times in a normal setup. Okay. So what we're going to do in this scenario is if I know that we got pi over 3 and 2 pi over 3, then I can kind of still use that. Okay. But in this scenario, since sine of 2x equals this, that's the same as saying 2x is equal to pi over 3, or 2x has to equal to 2 pi over 3. We want to consider both possibilities, but instead of just being x now, it's 2x equals to that. And that's okay because we're going to multiply both sides by 1/2. So that means I'm going to get rid of this. I get x is equal to pi over 6. And then same thing here, multiply by 1/2. So x is equal to, that'll be gone. It'll be pi over 3 now. Okay. But because of the periodic nature of this pi here, then that means if I go from here, I go one more pi above that. If that falls within this range, that's still going to be a solution here. So let me try that out. So if I take pi over 6 plus pi, which is the same as 6 pi over 6, I get 7 pi over 6. If I take pi over 3 plus pi, I get 4 pi over 3. Both of these values are in this interval of 0 to 2 pi. So that is how I'm going to get to actually 2 additional answers. Normally, if it was just solving this, I would get 2 answers here. But I'm not doing that here. I'm going to be doing sine of 2x. So my 4 total answers is going to be pi over 6. Whoops, not plus. Pi over 6, pi over 3, 7 pi over 6, and 4 pi over 3. Okay, that's what because it's 2x and we have a shortened period. So that's why we're going to repeat this value on this interval more times than just the normal 2. Okay, and I believe this will be one last example here. Projectile is sent off with an initial speed of v sub 0 of 350 meters per second and clears a fence that's 3,000 meters away. The height of the fence is the same height as the initial height of the projectile. The distance the projectile travels is given by this equation. Find the interval of possible launch angles to clear the fence. Okay, so I have v sub 0 is 350. I have distance here is 3,000. So the goal is, can I solve this equation? So we're going to treat it just like we did before. We want to isolate that theta as best we can. So 350 squared times the sine of 2 theta, all over 9.8. Okay, so I can start by multiplying both sides by 9.8 here. I do that, I'm going to get 29,400. I might as well go ahead and do 350 squared as while I'm at it. So 1,225,500 times the sine of 2 theta. From here, I can divide both sides by 122,500. Okay. I do this in my calculator. I'm going to use more decimal places, but just for writing purposes, this will just simplify to 0.24 for right now. And that'll be the sine of 2 theta. This does not have reference angles to work with, so we're not going to find an exact answer. Instead, we can use our inverse sine to both sides here. Okay, so if I do that, I'm going to get this. I'm going to get inverse sine of 0.24 is going to come out to 13.89. Okay, so 2 theta equals 13.89. But to remember what I'm doing with this one, if we're dealing with sine, there's two possibilities for my kind of a launch angle idea. When does that sine equal to 13.89? It's going to happen here, like this angle. So it happens at 13.89 degrees, but it also happens here. Okay, so this will also be 13.89 degrees as well. So that's where I get two possibilities for sine coming out to this value. So that, remember though, is actually 180 minus 13.89. So that's going to be 166.11 here. So what does that mean for our purposes? We're going to consider this possibility as well. 2 theta is equal to 166.11. So I do my normal solving for theta. I'm just going to divide both sides by 2 here. So theta comes out to 6.94 degrees. And my other theta will come out as 83.06 degrees. So what does this mean? It means that the range, the interval of possible launch angles, is any angle that's between basically 7 degrees and 83.1 degrees. Okay, the ball will clear as long as 7 degrees all the way up to 83.1 degrees. Anything in between works. If we're outside that range, it's not going to clear the fence. Okay, so that's what we found with these values. Okay, so this diagram does not really represent the launch angles here. Okay, but we use that diagram to help us find our two possible angle measures that might help with this. Okay, and that's it for today. Take care, everybody.